So basically, the idea of today's lecture is to complete the exercise that we started, well, last week, which regarded the description of this slider crank mechanism, and then move on to the next topic, which will probably, consist in the one of the last topics that we will deal with during this course, which is how finite element formulation cope with the formulations of problems encompassing multiple bodies. Okay, so how system of multiple bodies are typically treated within the formulation which resort to finite elements. Okay. In fact, I just uploaded a new chapter of the course notes that you can find is chapter 5, I guess. So basically that completes the material available for this part of the course. So without further ado, let's start. So as you may remember, I basically brought here in the board the last part of last exercise. So basically we were in the process of deriving the external forces acting on our mechanism, in particular the generalized, the expression of the generalized forces insisting on our mechanism. Of course, in this case, the only external force that actually insists on our system is gravity. But the idea is to see how this force is actually decline in terms of generalized components. And so basically, we resorted to the virtual work theorem, first deriving the virtual work of external forces. And then we were able basically to decompose this contribution into basically three various components associated, sorry, to the three different, let's say, categories which compose our vector of generalized coordinates. That's to say, the rigid coordinates associated to translation, the coordinate associated to rigid rotation. In this case, we are in the 2D plane, so we have only one coordinate for to describe the rigid rotation. Then we have the generalized deformation coordinates. And here we were basically in the process of describing these three quantities. So I leave you to actually derive these quantities, since everything is basically defined here, because this is just an identity matrix. A theta is basically the derivative of the transformation matrix, which we have Rg over by we already defined. And here on the bottom, we have basically the transformation matrix itself, insisting on the inertia shape matrix, calculated at x 0.5, y 0.5, because if you remember, here we were evaluating the effect of gravity, which insists, of course, at the center of mass of our body, which is located at x equal 0.5. Okay. So what is the last part of this exercise? Well, the last part consists in deriving the constraints, which is, if I don't recall wrongly, is number 6. So okay, so let's derive the constraints. And to do so, actually, let's see if I can import. Nope, maybe the previous one. Yeah. So let's again here the picture of our mechanism, where we have basically 4 bodies, 1, 2, 3, and body number 4, with the generalized coordinates defined for each of the two nodes. Well, what are the constraints for our body number 3? Huh? Can you guess? Well, basically, we have two hinges, no, at the two nodes. So we have to impose what? That body number two, and body number 3 have a hinge at point 2. And so there must be a coincidence of the position, while rotation must be free between the relative rotation. The same goes between body number 3 and body number 4. So to sum up, we have first, we have a point A where we have a hinge. And how do we describe this? We have that the position of point A, which can be described as such. The position, okay, well, in this case, it would be the position of the origin of the local frame of body 3. Okay, so this is something that we typically refer to as this. Okay, but if you remember, at the very start of this exercise, we dropped the superscript 3 for the sake of clarity, because basically we were only dealing with body number 3. Okay, so to ease out the notation, we decided to drop this. In this case, allow me to reintroduce it, since dropping it would be, let's say, maybe a possible source of confusion. Okay, so I will just put it in red, okay, so that it's clear. All right. And again, so the position of point A is basically the position of the origin of the local frame of body 3 plus A R0 over bar of point A, always expressed with respect to body 3. Of course, the first thing that is apparent from this description, what is it? That this quantity here is 0, right? Because point A is actually the origin of the local frame, okay? So this is A, let's write it. Point A is the origin of what? B1, B1, 3, B2, 3. Okay, that's why it's 0. But this also can be described, of course, resorting to the frame of body number 2. In particular, we can write down that this has to be equal to, sorry, this is 2, plus A2 applied over what? RA over bar, expressed in this case in terms of the local frame of body number 2. So in this case, R over bar A is not 0, okay? So let me write, for the sake of clarity, that this is not 0. Okay, in this case. And therefore, our first constraint reads as such. R3 is equal to R2 plus A2 R over bar A2. Okay, so this is the first one. So this is the first constraint. Okay. The same goes for point B. So it's kind of apparent, no? And so we have that at point B, you also have a hinge. And this basically tells us that at point, the position of point B, which is again R3 plus A3 R0, sorry, RB over bar 3, like so, must coincide with the same quantity expressed with respect to the local frame 4. Okay, but what is it RB for? It's 0, for the same reason as it was for body number 2. So this is 0. Oops. Okay, because again, it's the origin of the local frame of body 4. Okay, so yeah, I think everything is quite easy. But in this case, let's elaborate a little bit more. So we have what? That the position of point B at time t is equal to R. Sorry, let's actually, this is already written. The position, local position of point B with respect to the frame 3 can be written as what? As R0 B over bar, which is the position of point B with respect to the local frame of body 3 in its undeformed configuration, so prior deformation. And so we have a 3 here, plus, well, what we already know, so the deformation counterpart, that's to say psi, in this case estimated at xi equal to 1, because it's the end of the road, applied over QF. Okay. Of course, all of this is equal to 3 and 3 again, where this can be written as UB over bar 3. Okay? So this is the vector of the displacement induced by the deformation. Now, it's kind of easy to detect these two quantities. So R0B, what is it? Well, it's the end of the road, so it's basically L, which is the undeformed length of the beam, and 0, because it's a 1D, if you remember. How about this? Well, this, I think, can be written as such: 0, 1, 0, 0, 0, 0. Okay, and then you still have QF3, QF4, and QF5. Okay, and this, of course, gives, if you do the matrix multiplication, QF4, 0. Okay, and therefore, my RB over bar 3 is equal to what? To L plus QF4 and 0. Okay. Yeah, correct. Thank you, yes. And so now we just have to do the matrix multiplication. Which you can write in this way. We have that R3 plus A3 RB3 is all 3, which reads as such: R1, R2. I will put the superscript just later on. Cosinus of theta, then we have minus sinus of theta, sinus of theta, cosinus of theta. Applied over RB over bar, which we have just defined, must be equal to R1, 4, and R2, 4. And again, here we should have 3 written here, 3 written everywhere, theta 3, and here as well. Okay. So eventually, we have that my constraint equations at B read R1, 3 plus L plus QF4, 3 cosinus of theta 3 must be equal to R1, 4 and R2, 3 plus L plus QF4 sinus of theta 3 must be equal to R2, 4. Okay. And this basically closes the exercise. So you see, now we have gone through an application, an exercise, which is very simple, but in fact shows you in a practical way how to implement all the theoretical, findings that we have gone through so far. Now, and this closes basically this part. Now, what is the next part of the course that we would like to go through? Again, how all of this is actually implemented in a code where, as we know, we make use of the fact that a complete and exactly accurate description of the deformation is not possible due to the high dimensionality issue concerning all structural problems. As we have seen, the response, the answer to this question is the restricted formulation. Okay, but as you can see right now, also the application of the restricted formulation has issues. And in response to these issues, there are different answers, different approaches, and different formulation, and within the same formulation, different element types. Okay, so the next part of the course will be to describe to you, to understand how all these concepts are actually implemented into a code through the formulation of various approaches and different element types. Okay, and the pros and the cons which are associated to them. So we can basically name this part as such. Let's say finite element approach to multibody system. So let's write a short reminder on the restricted formulation. If you remember, we had that in general, as I was anticipating before, when we have a deformation process going on, in theory, given that the prerequisites associated to the continuity of the deformation process are respected, in theory, you should have that each point of the body can deform as it wants, independently from the neighboring points. This, again, would require an infinite number of degrees of freedom, of parameters, to describe the deformation of each point, being these points infinite in a continuum. Okay, this is a problem which is not resolvable this way. Okay, so we have to introduce an approximation. The approximation starts by describing this displacement field induced by the deformation, u over bar, which typically depends on the position of the point and the time. Okay, as basically a series expansion with an infinite number of terms, which resorts to a separation of variables, okay, where we have that the space contribution is separated from the contribution due to time or time dependent, where basically this is a basis, is a base function, with all the properties which are associated to base functions, so completeness, independency, and so on. And these are generalized coordinates. Now, let's say okay, at this point, basically, we have somehow described how this displacement field is composed, as a sum of infinite terms. Still, this infinite sum actually reflects what I was talking about before. So this sum is infinite, so it's a series, because infinite, as I was mentioning, is the number of parameters that we need to completely describe the deformation process in a continuum. Okay, so that's why we have infinite number of terms, because we would need an infinite number of parameters to describe the independent deformation of each point in the continuum. We cannot afford to do this, so we have to somehow restrict the problem, and that's why we introduce an approximation. What was the approximation? The approximation consisted in saying that, okay, my displacement field induced by the deformation is kind of equal to what? To the sum of not infinite terms, but to a number of terms n, which is finite. Again, with n number of the natural numbers. Okay. How do we choose this n? Well, that's actually quite a topic to go through. But let's say that we do this, and we have to say that in order to be able to do this, this series has to possess a number of properties that we have already gone through described. It has to be a Cauchy series and so on. All right, but so in this way, basically, we have kind of tackled the issue of dealing with an infinite number of parameters, because we can select this number. We can reduce it to the number that we want. Again, the number that we want eventually has to be selected somehow, but let's stop it here. But there is an issue with this. There are still two issues. What are these two issues? Well, first, this psi, which retains the dependence with respect to space variables of our problem, has to fulfill the boundary conditions, right? In the same way as this displacement field induced by deformation has to be compliant with our boundary conditions, natural and geometric. So in terms of kinematic quantities, displacement and rotations, and in terms of forces and moments. Okay, so this displacement field cannot be whatever, but a priori has to fulfill the boundary conditions. Since the boundary conditions are something which is associated to the domain of space variables, the boundary conditions which must be fulfilled by U fall now on psi. So all the psi variables must fulfill boundary conditions. And this is not a trivial thing. It means that this base function not only have to be a base function, they have to be constitute a base function, so they have to be complete and independent of each other. But they also have to fulfill the boundary conditions, right? So for example, if you have a cantilever beam which is fixed at one point, your function, one of these functions, whatever of this function, cannot have a value of the displacement different from 0 at the root. All right? So this psi must be selected in such a way that the boundary conditions are fulfilled first. So this is the first issue. Second issue, what are these QF? Meaning, what is the physical meaning of these generalized coordinates here? We don't know. Since this is general, it can be basically whatever function, given that it's a base function and that it fulfills the boundary condition. So how actually can I know what these are in terms of physical meaning? I make you an example that you should probably know. There is a way to actually select this psi, in which these psi are the mode shapes of your structures. Well, in this case, for example, the first of these for a cantilever beam can be something like this, because the first mode shape is something like that for your structure, right? But then, what does this coordinate, which is associated exactly to this shape function, mean? What is the meaning, the physical meaning? It's not actually very easy to tell, right? Because this is the coefficient in this series, depending on time, which is multiplied to this possible shape function, okay? But its physical meaning is not actually apparent at all at first. So these are the two problems. This must fulfill boundary conditions. The physical meaning of these quantities in this series is not really intuitive, okay? And what is the problem associated with the fact that the physical meaning of this quantity is not apparent? That it's not easy to judge if their values are appropriate or not. If you don't know what they represent, how can you tell if they are correct or not? Okay, that's the real problem. So in order to try to solve these issues, these two issues, they introduced a formulation, which is the finite element formulation, the finite element approach, which resorts to the use of particular set of shape functions. Okay? So These are called shape functions. And so, as I was mentioning, we have two issues. First, the psi must fulfill the boundary conditions. Let's recap it of the structure. Second, I just wrote 3. The physical meaning of the QF is not clear. All right. So, again, as I was mentioning, there was a proposed solution to this. We introduce the finite element shape functions which are also known as hat functions. So, also known as hat functions. Why hat functions? Because they are made like this. So how? They are 0 in all the domain but at point P, okay, of interest. Or if you want, at node K, okay? Okay. And secondly, they assume a value of 1 at node K. Okay? They are typically written as such. In fact, they are indicated this way. Psi, just like we had before, K over R0 with an overhead. That's why they are called hat functions. Why are they actually, what is the advantage of this? Of these 2 points? Well, they actually address the problems that we have. Because since we have point 1, since they are 0 everywhere but at a point, they automatically fulfill all boundary conditions. Okay? Right? They are 0 everywhere but at a point where the node is. So if I want to fulfill, if I want, the structure to have a particular value in terms of displacement, of rotation, or whatever, at a particular point, I just need to give the value of the coordinate associated to this, the value which I want, because everywhere else that is 0. And in the point, it values 1. So if I want, for example, if I'm expanding the displacement and I want the displacement at a certain point, at a certain node, to have a value of 10, I just, all of the rest, in all every point, I'm okay. And then I get the shape functions associated to the node, which is exactly located at the position of interest, at the boundary, for example. Then I give to the generalized coordinate associated to this the value of 10, because this, in that correspondence, is 1. Okay? So this basically solves the issue of the boundary condition. So the boundary conditions are satisfied automatically. Again, why automatically? Because it leaves to the appropriate quantity, to the appropriate value of the coordinate associated to each shape function, the task of complying with the boundary conditions. Okay? All right. Then, point number 2. Since they have a particular value of 1 at the node k, it means that the coordinate associated to that particular shape function exactly represents the quantity, the value of the quantity which I'm expanding at that point. Okay? So if I'm expanding the displacement, qk will be, so this qk here, qfk will be the value of the displacement at node k. Because this, all the other contribution at node k are 0 by definition. The only one which does not vanish is the one given by pk. Okay? And pk in that particular node k values 1. And so, basically, the value of u at point k is exactly this. Okay? That's why I'm actually giving an example here. But let's actually write it here. The QKF represent the quantity which I'm expanding, the exact value of the quantity I am expanding at node k. Okay, and therefore its physical meaning becomes clear. Okay? Again, let's make an example, but this is probably best if I move it here. So, example. Again, you see, this is a cantilever beam. Huh? Cantilever beam. Okay? So look at this. You see, here you have a displacement field induced by deformation. In this case, since we have a cantilever beam, there are no rigid rototranslation allowed, no? So the system is not labile, it's isostatic, right? Okay. So all the displacement induced by a rigid motion is 0 here. We only have u over bar, the field of displacement induced by deformation. Very well. Now, what are we actually doing when we use the psi? And here, why? That's why I'm actually. So these are the psi. There is an overhead here. What I'm doing is the following. I'm discretizing the structure. How am I discretizing the structure? By truncating the series. So in this case, n, and I'm writing the following. Here, n is equal to 5. You see? So, again, please have clear in your mind this concept. Truncating the series means discretizing our continuum structure. That's what we do. That's where nodes and all, meshes and all those terms come from. They all come from a truncation operation. Okay. So here we stop at 5. Again, the topic of investigating what is the proper value of this n can be taken in a whole class, but still, you see, these are the various shape functions. So for example, here I have the first one is this one. You see, we have 5 nodes, which are this one. 1, 2, 3, 4, and 5. So these are all nodes. Five nodes. Each node has its own shape functions. So shape function number 1, in this case, head functions, is this one. 1, then goes to 0 at all the other nodes, and then stays 0. Okay, this is psi1. Psi4, in the very same way, what is it? It's 0 everywhere, then it goes up, and then it goes down again. And the value they assume is 1. You see, all of them. So what is the meaning here now of QF1? Is the displacement at point 1. So you see now that the physical meaning of these quantities is not anymore confused. It's very clear. It's a displacement. And then this is very important because you can actually say if the value that they assume in your analysis has sense or not. If you want to impose some requirements to your analysis, how do you actually impose your requirements? You have to impose your requirements, for example, to the values of the displacement. For example, if you do a static analysis, you have your cantilever beam, which can be, for example, the simplified representation of a wing. You fill the wing with fuel when it's standing on the track, and you say, I don't want my wing to deflect more than a certain value. Okay, so your requirements is imposed in terms of physical quantities, as it's natural to be, right? But in order to impose these requirements on a natural quantity, you have to be able to express your numerical solution in terms of quantities which have a physical meaning. That's why it is important to be able to adopt a formulation in which these coefficients of the series of expansion have a physical meaning. Okay? And that's an advantage of using the so-called head functions or finite element shape functions. Okay? All right. Now, this finite element approach, which is, again, nothing else than the restricted formulation making use of this particular set of shape functions, as I was saying, is characterized by various formulations and within the same formulation of various element types. Okay? So, we have that the finite element approach consisting various formulations What is the main difference among these various formulations? They basically differ with respect to the frame of reference that they consider to implement their description of the displacement field. What is the meaning of this? Some of them, for example, make use of the inertial frame as frame to describe the displacements of the various elements. Others make use of different element frames, local frames. Okay? Okay, so we can say that here that they differ with respect to the choice of the frame considered to describe U. Okay? Or if you want, the displacement of the element And then, within a formulation, there are various element types. Okay, and what is the difference between various element types? Well, they differ with respect to the quantity which they represent at the nodes. So displacement, rotation, positions, okay? So they differ with respect to the choice, or if you want, the type, the kind of quantity that they represent at the nodes. Okay? All right, so let's start the first description of a first formulation, which is the absolute nodal formulation. Which refers to the inertia frame. Okay? So it refers to the inertia frame. And within the absolute nodal formulation, we will describe a particular set of element type, which is called isoparametric element. So actually, let's write it like this. This is, let's say, so the first element type that we're going to describe within the absolute nodal formulation. Okay, so we are within this formulation. Within this formulation, we are going to describe the isoparametric elements. Does someone know why they are called isoparametric? No idea. Have you ever heard of this kind of elements? So, same type. So iso gives you a hint, no? Isoparametric. So the same parametrization for what? Well, they are called isoparametric because they use the same parametrization to describe various quantities within the element. So for example, the displacement and the position of a point, of a node within the element, they are interpolated using the same parametrization. Okay, so the same functions are used to describe position or displacement of a same point. That's why they are called isoparametric. Okay? Okay. And in this case, we are going to analyze a very simple one, which is the 2D rectangular element. Okay, which I should be able to describe here. Now, which one is it? Should be this one. Yes. Okay. So, what are the hypotheses which are at the basis of this element type? We have the displacement and positions are used as nodal quantities. And the important thing to note here is that no rotations are included. Okay? So it means that, again, if you remember the topic that we went through a couple of lessons ago. So basically here, again, when I am interpolating, when I'm actually truncating and expanding in series my displacement field, what I'm doing is discretizing and interpolating my solution. What does it mean? It means that I want to reconstruct, in this case, the displacement induced by deformation at a point within my structure, given the knowledge of those quantities at the nodes. So I know these quantities. I solve the dynamical equations. I'm able to basically get the values of the generalized coordinates, QF, at the nodes. Given this knowledge at the nodes, adopting a certain type of element formulation, I'm able to reconstruct the same quantity, that's to say, in this case, the deformation field, at each point in my structure. Okay, that's the idea of a finite element model. Okay. In so doing, when I use these element types, the only QF that I use are displacements at the node or positions at the node, no rotations. Okay? Okay. So, as basically we always do, we assume, for example, that this quantity here, so basically the length of my element is, let me check. I think I called it B, yes. This is 2B, okay? Here I have that so you can see basically two coordinates. The element, the inertial coordinate, the inertial frame, x1 and x2. And then I have a new coordinate system, which is not B, but it's I1 and I2. I1 and I2 is the frame of the element, okay? Which is, in this case, located at its center. And the dimension of my element in this undeformed configuration, before the deformation, which is represented in the drawing in A, has this following dimensions, 2B, and here should be C, if I'm not wrong, 2C. Okay? Okay. So, as I typically do, as I did actually in the exercise before, I have to assume a certain expansion to represent, in this case, the position of the nodes. Okay? So let's do it. assume, let's say, functional dependence. Slide it. The solution, or of the nodal quantities, with respect to the space coordinate. Because here, my goal, what is it? Is to derive what? The shape function, the finite element shape functions of this element type. Okay? So as we have seen before, let me slide it. Here, this example, we had basically a certain number of psi. So the knowledge of the psi basically characterized completely my parametrization. Okay? So here, I had different elements. This is one element, this is the second element, third element, fourth element, fifth element. Okay? I have 5 elements, and each of these elements has a certain parameterization. These are 1D elements in this case, right? Well, these element types are characterized by a certain value, a certain quantity which are associated to this, which are these shape functions here. So what I'm doing now is actually try to see what are the shape functions associated to the 2D rectangular isoparametric element associated to the absolute nodal formulation. Okay? So if you want, I can write it here. What is the thesis? What are the psi associated, or which define this element these are what we are trying to see. So in so doing, we have to first assume a functional dependence of the nodal quantity with respect to the space coordinate. Okay, which equals in assuming the physics, as we have already done. And so I have that the position of a point P, in particular the coordinate associated to x1, as a linear expansion from considering polynomial expansion. So we have A0, then we have A1, then we have, so in the local frame, what we had before, if you remember, was R01, for example, no? R0 over bar, which was the position, in particular the coordinate associated to B1 of the position in the form configuration of a point within my body. Here, I don't have any more R0 because I'm not considering anymore the whole body, but I'm only moving within an element. Okay? So I don't use R0, I use X over bar. 1, 0. Okay? Which again, you see, it's the position of point P in its end-form configuration and which is described by P0. Okay? So this is this. Okay? All right? So basically, I am moving within my element using the local coordinate of the element frame, which is x over bar. Okay? So if you want, you can write this. X0 is the coordinate associated to I1 and I2 as R0 over bar was associated to B1, B2. That's it. So there is a clear, let's say, parallelism. But of course, it's not ending here. So I have A2, which is this third coefficient, x2, 0, plus A3, x1, 0, and x2, 0. So please note that x1 and x2 are the coordinates along I1 and I2. And as you can see, I'm saying that here the functional dependence on the horizontal coordinate or the horizontal component of my position, which is P1, described with respect to the inertial frame, has a functional dependence on the position of the point expressed with respect to the local frame of the element, which is symmetric with respect to x1 and x2, 0. And this makes sense, basically, no? Because there is no physical meaning which would support an asymmetric dependence on x1 or x2. Okay, I have a rectangular element. Why should I say that the position of a point with respect to the horizontal coordinate should have a preferred dependence or x1 on x2? Huh? There is no physical meaning. That's why I'm actually assuming this. Okay. Okay. Then the same goes for P2, for the vertical component of the position of a point within my element. And I assume it to be like this. x1, 0. So you see, apart from the coefficients, which are of course different, the functional dependence is the same. Again, because this reflects the symmetry of the element, if you want, no? You see, the element is symmetric, all right? So I assume that when I have to interpolate the displacement, in this case the position of a point after the deformation, given the knowledge of the deformation, the position of the nodes, I shouldn't give any preference to the nodes here, or to this, or on top or on bottom. There is no physical meaning to justify such an approach. Okay, all of this can be basically written in this term. P, the vector of position, is equal to a matrix phi applied over vector A. I want you to note one thing which basically characterize the fact that we are within the absolute nodal formulation. You see, so here you have. Let's actually write it here clearly. So this is the element frame. One. Okay, I1, I2. These are the nodal coordinates. Okay. If you see, in the reference configuration, okay, I assume them to be originally parallel with respect to the inertial frame. But when they are deformed, so when the element is deformed, the quantities still are parallel to I1, I2. Why? Because in the absolute nodal formulation, the nodal quantities are always referred to the inertial frame in whatever condition. So the fact that these arrows here, which only depicts the quantities, that's to say the position of each node, stay always with the same orientation of I1 and I2, is a consequence, direct consequence of the fact that I'm within the absolute nodal formulation. Okay. So you see, it's actually, well, whatever. Yes, let's do like this. Okay. Because they're always parallel to this and to this, as they were here, and also in the deformation. Okay. All right. Now that we have clarified a couple of terms, let's go back to this expansion. And again, we assume a symmetric expansion in x1, 0 and x2, 0 for both P1 and P2. Why? Again, no physical reason to introduce asymmetries. Okay? And again, we have just rewritten this expansion in a matrix form. Okay? In particular, you can write the following, that our vector A is the vector of coefficients 0, 1, A2, A3, 4, A5, 6, and 7, and that's it, transposed. sorry, yes. And then our psi is the vector, is the matrix of functional dependency, okay? So it's basically 1, x1, 0, x2, 0, x1, 0, x2, 0. And then we have 0, 0, 0, 0. And here the same. 1, x1, 0, x2, 0, x1, 0, x2, 0. All right. Now, how do we determine the vector of the coefficients? In the same way as we have done in the exercise that we have just completed. That's to say, by imposing the position vector P, when estimated at the nodes, gives exactly the nodal quantities. Okay? So, to determine the vector A, we impose that P equals the nodal quantities of the nodal coordinates at the node positions. So what I'm meaning here is that P1 of minus B minus C let's go and check again the picture. So P1 of minus B and minus C, what is it? It's this one, right? Is the position, horizontal component of the position of node 1. This must be equal to what? To E1, right? By definition. So let's write it down. This is exactly E1, okay? And the same goes for all the other quantities. So P2 of minus B minus C is E2. Okay? Then again, we have that P1 of B minus C is equal to E3. P2 of B minus C is equal to E4. P1 of B, C is equal to E5. P2 of B and C is equal to E6. P1 of minus B, C is equal to E7. And P2 minus B and C is equal to E8. Okay? So, please note that it's not a case that we had an expansion with 8 coefficients to determine. Why? Because we had 4 nodes, okay, with 2 quantities each. So what is the meaning of this? The meaning of this is that if I wanted, I could increase the order of the polynomial expansion, including 9, for example, or 10 coefficients. But this would have meant that I should have increased the number of the nodes of my element. I should have had more information on my element. Okay, so that's why, different elements have, for example, a higher or a lower number of nodes. This most frequently depends on the order of the interpolations that you provide. Okay. Okay, so it was not just by chance. Okay, so in matrix form, we write that E is equal to psi over bar equal to A, where E, again, well, I write it just for the sake of clarity, but I think that it should be clear already, is the vector of nodal quantities. Okay. So we have the following. And then we are about to stop. On one hand, we have this, which is the expansion that we assumed. On the other hand, we have that E and from the second, you can derive that A is equal to psi over bar to the minus 1 applied over E. Okay? And the consequence of this what is it, the consequence of this all? That P is equal to psi applied over psi over bar to the minus 1 applied over E. Right? And guess what? This is a matrix that expresses the position of a point within my element with respect to the nodal quantities. So that's actually my psi. It's my finite element shape matrix. So again, okay. So last, Let's actually find out what they are. We have that. Okay, this is a little bit annoying, but let's do it. Bless you. 1, 0, 1, 0, 1, 0, 1, 0, 1, 2, 3, 4. I think it's fine. Yes. Minus B, 0, B, 0, B, 0, minus B, 0. Minus C, 0, minus C, 0, C, 0, C, 0. Then we have BC, 0, minus BC, 0, BC, 0. Yes, sorry. BC, 0, minus BC, and 0. And then once again, 0, 1, 0, 1, 0, 1, 0, 1. 0, minus B, 0, B, 0, B, 0, minus B, 0, minus C, 0, minus C, 0, C, 0, C. And then last, 0, BC, 0, minus BC, 0, BC, 0, minus BC. Okay? So as you can see, this is a square matrix, an 8 by 8 square matrix that we can invert, okay, as we did. The next slide. So if you do the computation, what eventually get is this element-shaped matrix for the rectangular 2D element in the isoparametric element in the absolute nodal formulation, which has the following structure: n1, 0, n2, 0, n3, 0, n4, 0, 0, n1, 0, n2, 0, n3, 0, and 4, where n1, which is 1 over 4 BC times B minus x1 over bar, C minus x2, 0 over bar. Then you have n2, which is equal 1 over 4 BC, B plus x1, 0, C minus x2, 0. Then you have n3, which is 1 over 4 BC of B plus x1, 0 over bar, C plus x2, 0 over bar, and then finally n4, 1 over 4 BC, B minus 1 over bar 0, C plus x2, 0 over bar. Okay? So this is the matrix, the shaped matrix, which characterizes this element type. Okay? Now, next time, what we will do is we will introduce another type of element, and then we will see why these two element types are used or not used, and why eventually we will have the need to resort to another formulation other than the nodal absolute formulation. Because as we will see, the other type of element that we will describe next time generates misrepresentation in terms of the energy content of this element when associated to this element formulation. It means that, as you will see, that it kind of introduces a fake strain energy in the element, even if the element, even if the body is not suffering any kind of deformation. So even if you have a rigid rototranslation, the other element type that we will describe fakes a strain energy, which shouldn't be there. Okay? Okay, this is it for today.